Alright gang, so for this next video we're going to be continuing to talk about stereochemistry. And the next thing we're going to take a look at is how do you experimentally determine if you have enantiomers, right? And the way to do that, and I mentioned this in the previous video, is have them interact with plane polarized light, right? Because I mentioned enantiomers, while physically they don't have any different properties, optically they are different, right? So we can call them optically active. And how this works is if we take plane polarized light, and by that I mean light of a singular wavelength, and transmit it through a sample with a chiral molecule, kind of like shown here, the analyzer at the end of the instrument can detect how the light has rotated. Because a chiral molecule will rotate light in a certain way. So chiral molecules can rotate light one way or the other based on its chirality. So if you have a sample with entirely one enantiomer, you'll end up getting rotated light in a either clockwise or counterclockwise fashion, right? Positive or negative. If we have a racemic mixture, so an equal amount of two enantiomers, there is no optical activity, right? Because one enantiomer will rotate the light one way, and the other enantiomer will rotate the light the other way, canceling each other out. So you'll see this terminology used sometimes. But clockwise light rotation is called dextrorotatory, so a positive sign, and counterclockwise rotation is called laboratory, so a minus sign. And what's important here to note is there is no relationship between R and S, right? We can have an R molecule that is either, as shown here, positive or negative. It can rotate light either way. Remember that R and S is just the way that we name the chiral center in order to talk about it. Plus and minus come from experimental determination. Okay? So what if we have a molecule with more than one chiral center, right? What's the situation here now? So one thing we can do, right, is if we have a molecule with more than one chiral center, we can think about, or we can know just by a mathematical standpoint, how many different molecules we have. So essentially, we just take 2 and do it to the power of n, where n is the number of chiral centers. Okay? So for example, if we have if we just have one molecule with one chiral center, and n equals 1, right? 2 to the power of 1 is just 2, and so we only have 2 stereoisomers, right? 2 enantiomers. And so what happens next, right, is if we have 2 chiral centers, right, what's the situation there? So then we run into something called a diastereomer, okay? And these are non-mirror image stereoisomers, meaning stereoisomers with some chiral centers that can be the same and some that are different. And diastereomers, unlike enantiomers, they do have different properties in different physical environments. Okay, so let's look at this first molecule here, and we'll show some examples of diastereomer. So first off, let's take a look at the enantiomer of this compound. Okay, right, and all we're doing here is just changing, essentially, the orientation, the spatial orientation of these bonds. So where the OH was on a wedge before, now it's on a dash, and this dashed amine down here is now on a wedge. Okay, and so the chirality for these molecules are R and S, at least for the first one, right? So when we switch these chiral centers up, we know that the configuration changes as well. So the first chiral carbon is S, and now the second one is R. And we'll go through the priority here, but it might be good practice to try to do this on your own, okay, to try to get that configuration that I showed here, okay? But nonetheless, right, changing the orientation, right, changing 2 of the groups around. So the OH is on a dash and the hydrogen is on a wedge, even though we're not showing it, and the same for the amine down below. It's on a wedge and the hydrogen is on a dash, which is the opposite for this first molecule, right? So these are enantiomers, right? Because every chiral center is opposite, right? So what if we change this now, right, and had, instead of, right, both chiral centers being different, what if only one of them was different? Right, we'll keep this amine on the wedge, and we'll have the OH now on a dash. Right, meaning that this is R, and this is R. Right, so these are no longer mirror images, right, because only one chiral center is different, right, and the other one is the same. So these are diastereomers. Right, and the same can be said for these two, right? These are also diastereomers. And so lastly, if we drew this molecule, right, once more, with a different stereocenter in one location, right, but kept it the same in a different location, we now have another set of diastereomers, right? Where we have, right, these two molecules as diastereomers and these two molecules as diastereomers. And these two molecules are enantiomers. Right, so this whole sort of slightly complicated relationship happening here, right, where we can have a set of diastereomers and enantiomers in the same molecule, right, because we have this formula here where, right, we have 2n and n equals 2, because that's the number of chiral centers, as we see up here, so we know that we need to have 4 stereoisomers. And that's exactly what we have down below here. We have 4 different stereoisomers. We have RS, SR, RR, and SS. Okay? So take a minute if this is sort of confusing and try to convince yourself of this fact, right? Look at these different molecules and determine which are enantiomers and which are diastereomers, right? Molecules with opposite chiral centers are enantiomers, and molecules with only one chiral center opposite and the other is the same, right, or any variation thereof, right? We'd have more chiral centers and have even more diastereomers and enantiomers, but that gets kind of complicated to draw. But for every stereoisomer, there is an enantiomer, and the other stereoisomers in the set are diastereomers. And we'll take a look at more example of these, right, to sort of clear up any mental glitches we have with this concept. So the last thing we'll talk about here is something called a mesocompound. So mesocompounds are compounds that have chiral centers, but are not actually chiral. And so what that means is if we have a mesocompound, right, with 2 or more chiral centers and a plane of symmetry, in addition to other enantiomers and diastereomers, it is a mesocompound. Okay? And so we'll talk about what that means down below. Right, so we have this cyclohexane here with 2 methyl groups, right? The wedges and dashes aren't drawn in yet, so we'll go ahead and do that. So looking at this first example here, right, let's have the methyl groups on wedges. Right, and we can see here, right, this is a chiral center because we have a hydrogen on the dash, a methyl group on the wedge, and one portion of the ring, right, is different than this portion of the ring, right? Because this carbon is bonded to 1 carbon, 2 hydrogens. This carbon is bonded to 2 carbons and 1 hydrogen, right? So this is a chiral center, right? But it is a mesocompound because there's a plane of symmetry down the center of this molecule. You see that? So we can fold this thing up on itself, right, like a sandwich, and both sides would connect. And we can kind of convince ourselves of this fact, right, by trying to draw the mirror image of this molecule, right, like we did in the previous video. But when we try to do that, what ends up happening is we do actually have this same molecule again. Right? Because right now, right, it looks like, yeah, they're mirror images, and typically if we try to rotate a molecule, we end up not being able to superimpose one on top of the other. But as we can see here, if I rotate this molecule, right, despite the groups being upside down, right, we can superimpose this on top of itself, right, and get the same exact molecule, right? They're superimposable. So this is what we call a meso compound. Right, and you might be thinking, oh, okay, well, we did the mirror image, but what happens if we turn the wedge bonds to dashes instead, right? Because that should be, hypothetically, the same thing. So if we try to do that, right, even though right now it looks like, right, we can't superimpose them on top of each other because the dash bonds, right, pointing down, the wedge bonds pointing up, that wouldn't match. But what's interesting, right, because we have that plane of symmetry, right, going through the middle of this molecule, what we can actually do is we can rotate this whole thing by 180 degrees, right? We can just turn it on itself, right? And so if we do that, right, because the dash bonds are pointing down, now they're pointing up, so they're on wedges. And to sort of make things visually make sense and spatially make sense, let's say this is carbon A and this is carbon B, right? When we flip this molecule on itself, carbon A ends up down here and carbon B ends up on the other side. Right? So even though, you know, we've labeled these carbons differently, they are exactly the same chemically, so it doesn't matter which is carbon A, which is carbon B. But when you flip this on itself, that's where the bonds end up. Okay? And so we can see we end up with the same exact molecule as above, right? So this is a meso compound. Okay? And so what that means in terms of numbering things, right? Normally we say 2n, right? And if n equals 2, if we have 2 chiral centers, we should have 4 different stereoisomers. But with a meso compound, right, because we have one meso compound in this mixture, we actually only have, right, 3 different stereoisomers. Okay. So what we're going to do next is look at some different examples of more molecules, some with symmetry, some without, and we're going to try to determine which of these molecules are meso compounds. Okay, to kind of get good at looking at a molecule, knowing whether there's symmetry, what that means, and what we can kind of determine from that fact. And we have another example here where we'll just look at how many stereoisomers are possible in tartaric acid, so we'll go through these examples together in class.